One of the first things taught in algebra class is the graph of the parabola. This is the parabola y equals x squared. In this parabola, there's clearly one point in which the function equals 0, at x equals 0. These zeros, or roots, are the points at which the polynomial p, given our point x, is equal to 0. But not all parabolas have a 0. In this example, y equals x squared plus 1, there's clearly no 0 as the parabola sits nicely above the x-axis. And we just accept that understanding of polynomial roots, but eventually we learn of imaginary numbers of the form a plus bi. And now our equation y equals x squared plus 1 has two zeros, two imaginary zeros of the form a plus bi. See how at x equals I, we get y equals I squared plus 1, which is the same as negative 1, right, because I is the square root of negative 1, plus 1, which is 0. Therefore, y equals 0 at x equals I. Now consider the polynomial p of x is equal to x squared plus 5x plus 6. We can factor this polynomial into two terms like this. P of x is equal to x plus 3 times x plus 2. To see why this is, we can distribute the two monomials and we end up with x squared plus 5x plus 6, the polynomial we started with. Now, let's try factoring our past polynomial of p of x equals x squared plus 1. It turns out that if we know the zeros of a polynomial, we can find the factored form. Now, recall that the first zero was I, and I'll just tell you, the second zero is negative I. Now, because of those two zeros, the factored form is p of z is equal to x plus I times x minus I. See how in this form, if x is equal to I, then because there's a term x minus I, that term would go to 0 because it's I minus I, and that 0 would multiply by the other term and would output 0, just as we said because I is a 0. The fundamental theorem of algebra states that every polynomial of degree n has n zeros over the complex numbers. Now let's go over what that means term by term. Let's start with degree. Degree is the exponent of the polynomial's variable. In this case, it would be 5, as 5 is the largest exponent on any of the polynomial p's variable, which is x. The next term is n zeros. At first, you would think the number of zeros is the number of x's such that p of x is equal to 0. But that's not quite true. Consider p of x equals x squared. This polynomial has degree 2, but it clearly only has one 0 at x equals 0. Even on the complex numbers, there's no other distinct 0 other than x equals 0. But imagine representing p of x equals x squared as p of x equals x plus 0 times x plus 0, which distributes to x squared, but has two individual terms. So the fundamental theorem of algebra is really making a statement about the factorization of a polynomial and how many unique terms it has. This says something about the two equivalent forms for every polynomial. And I mean, that explains why it's so quote-unquote fundamental. Because if polynomials are one of the most important objects in algebra, we want to know about their representation. Now, let's go over some notation. P of z is a complex polynomial, and the absolute value of z is equal to the magnitude. The magnitude of a complex number, as shown here, is its length, or the length of a triangle with sides a and b of a and bi. To calculate the magnitude, we simply use Pythagoras' theorem. So the magnitude is the square root of a squared plus b squared. Now this magnitude function is going to be incredibly useful because if the magnitude of z is 0, then z must be equal to 0. We are going to make a new 3D graph with a z-axis, x-axis, and y-axis, such that the z-axis is equal to the absolute value of p of x plus yi. Here's an example. Here's the graph using p of x equals x squared plus 1. There's the x-axis, y-axis, and z-axis. As you can see, our y has 2 points here and here. In fact, you could call those zeros. Now, as I showed before, with the fact that if the magnitude of z is 0, z equals 0, this means that those 2 points where z equals 0 actually are zeros, which makes sense considering those points are negative I and I respectively, as y is the imaginary axis, and this graph has roots at I and negative I. So finding zeros in this graph is the same as finding zeros in the complex plane. What you might have noticed about that graph is that the absolute value of p, or the graph, seems to strictly go up as you go out. I mean, look how all paths from the zero go directly up. So let's start with a simpler question. Here's our new question. Does every polynomial that is not constant have at least one zero on the complex numbers? The constant polynomial p is such that p of z is equal to an unchanging c. Now, surprisingly, this new question is equivalent to the fundamental theorem of algebra, aka if we prove this question, we prove the fundamental theorem of algebra. Now, recall this polynomial. We showed that these two terms represent two unique zeros. So let's graph this polynomial. This polynomial is p of x equals x squared plus 5x plus 6. Now, there are two roots at -2 and -3, or p of x equals x plus 2 times x plus 3. As you can see, the red and blue graph are the same. So this factored form is correct, and it has the same roots at -2 and -3. This is because if you make x, for example, -2, then -2 plus 2 is 0, and 0 times x plus 3 is 0. And so it's a root. Because we can represent p of x as x plus 3 times x plus 2, we can divide p of x by one of these terms. So p of x divided by x plus 3 is equal to x plus 2. We just reduced the complexity of this polynomial. And if you look here at this exponent, we also decreased the degree by 1. Because we said that every polynomial that is not constant has at least one zero on the complex numbers, our argument will work like this. Let p of z be a polynomial of degree n. If that polynomial is not constant, there is a zero. Now divide by it. And when we divide by that zero, we will get a new polynomial with one less degree that doesn't include that term. Now notice that our polynomial is of degree n. Then remember the constant polynomial where p of z equals c. Now think of the constant polynomial as a degree 0 polynomial because c is multiplied by x to the power 0. So it's degree 0. Now if p of z is degree n, that means it's not constant. Because it's not constant, we can find a 0. And because of that, we can divide by that 0. And when we divide by it, we get a new polynomial with degree n minus 1. And on top of that, we will have discovered one more 0. Each time we run those sequence of steps, our degree is going to decrease by 1. And the number of zeros that we've discovered will increase by 1. This process can only repeat while the degree is greater than 0, because it can't happen to a constant polynomial. So this process can only happen until the degree goes to 0. If we start with degree n, and each time we run the process decreases that degree by 1, and we can only go till 0, then the process can run n times. And each time we run the process, we get a 0, so the process discovers n zeros. This process only relies on this theorem, and this process shows that we can find n zeros on an n degree polynomial, because we basically keep iterating that process over and over again until we find those n zeros. And that proves that if we can prove that other question, we can prove this. Basically, it proves that they're equivalent. This form of logic is called inductive reasoning. Basically, because we can prove that after one step, we can make it to the next step, we prove that we can make all the steps. This theorem is the thing that proves that we can make it to the next step. It lets us continue to divide. Because we can keep dividing, we can divide until there are no more zeros left. And this lets us count the number of zeros there are. But even though we have simplified what we need to prove, still, proving this statement is incredibly challenging, and you don't really see how to do it. At least I don't really see the next step. In order to prove that statement, we're going to look back at this graph. Now, remember the observation we made. In this graph, there's a very strange property, and that is that it seems to always go up. As you go out, as you go away from the center of the graph, it always goes up. The z increases. So let's formalize that. We can go down. Now, this line of logic is very similar to that induction that we used earlier. Basically, imagine standing at this mountaintop and then looking down. Because you have a step that goes downwards, you can always go down to the base of that mountain. You can keep taking those steps until you get to the base, and in our case, the base of the mountain is 0. So proving that we can go down, in turn, proves that there is a 0. Even more formally, what we're going to prove is that in a disk D of radius r around a point A, there exists a B such that the magnitude of P of B is less than the magnitude of P of A, where B is in that disk, D. So we start at point A, and we can look in a little circle around us. The circle wrapped around the mountain. Now, we can guarantee, we're going to prove, that in this circle, there's a point B. Now, it doesn't have to be on the circle, it can be inside it, whatever. We're going to prove that there's a point B such that the height of B is always less than the height of A, or the magnitude of P of A. Then we can make B our new A, and we can draw another circle around B and find a new lower point, a new B. And we can keep doing that until we get to the bottom. Basically, we keep finding lower and lower points until we get to the bottom, as we said. This logic works because from our earlier statement, we can always find a lower point unless our magnitude is equal to 0. And as shown, magnitude is length, so it can't be less than 0. And since we can go down unless we're 0, as shown here, eventually our process must come to an end, and the only place where that could end would be 0. So our process must take us to 1, 0. To further show this, imagine this is this polynomial, which I added a little lip to, is a half ball. If you drop a ball down, it's going to keep rolling until it reaches 0. Let's show this again on a ramp. We draw a little circle around ourselves, and we know that we can go down. Then, from here, we draw a little circle, and we know we can go down. We draw a little circle, and we know we can go down. Even if we go off path, it doesn't matter. We know we can go down. But how do we prove that we can always go down? Right? Because that's what we need to prove. Well, we use a proof method called construction. Basically, we find the point. We find a point B that is less than A. In order to do this, we use things called roots of unity, as shown here, which are complex numbers of magnitude 1. And then we analyze the dominant terms of a polynomial, and we find that on a very small disk around A, or very close to A, our point, terms with smaller degree are larger and they're more dominant. Basically, they affect the polynomial's value more. And that's the overview of the proof. I love this proof. It combines things like visual intuition and physical understanding with proof techniques like induction. I think this was a great first YouTube video. Thank you for watching, and I hope you see the next video where we show all the algebra for the full proof.